to share with you the battery management systems and how one can efficiently model, simulate, or predict the battery systems as a whole. As you all know, electrification is a major trend, and the battery, the power electronics, and controls along with that is one of the key technologies that we have to use today to become more efficient in delivering the better technology to our end customers. Without further ado, I will hand it over to my colleague, Christoph Kammer, who is a technical expert in this domain. He will walk you through the battery systems modeling, simulation, and controls. Christoph, please take it away.
Thanks so much, Raghu and Christian. So hey, welcome everybody. So yeah, I'm Christoph Kammer. Thanks for a nice introduction. So I'll just get started right away. In the next hour or so, I'd like to give you a bit of an overview of what's been happening at MathWorks when it comes to battery systems modeling, simulation, and control. That's the overarching topic of today. If you're not familiar with MathWorks, the main product we make is MATLAB. It's a programming language as well as an IDE, and it's been around for now 40 years, 45 years, something like this. Yeah, it's started out as a tool to do data processing, numerical computing, visualization, and then over time we added on a large number of toolboxes for controls, AI, power electronics, and one of the main add-on platforms is Simulink, which offers this graphical environment to do dynamic simulation, multi-domain modeling, and enables a workflow which we call model-based design. Nowadays, there's around 5 million users using our tools, MATLAB, Simulink, and the add-ons. The main focus initially was in automotive aerospace. So all the top 10 companies use our tools, but it also branched out now to, yeah, pretty much any sector in the industry. For you specifically interesting, I guess, is energy production, for example, of course, automotive, with all the electrification of cars, railway systems, and so on. So electrification of everything, it's one of the mega trends which we have identified already, I think, yeah, 5 or 10 years ago. This started at MathWorks as one of the major development focuses, I'd say. Of course, one of the big pushes in this direction is renewable energies. Wind, photovoltaics is coming in strong, and it's posing quite a lot of challenges for our energy supply, specifically storage is a big topic, and that's again where, of course, batteries start to play a key role. Electric vehicles is the other one, cars, maybe at some point airplanes as well. At least there's at least one Swiss company I know of in Vale building short-range electric aircraft, which already work. And electric motors start to appear in, yeah, anything nowadays. So that's the three kind of main branches, I'd say, of electrification. And key technologies in electrification are, of course, again, batteries, power electronics, kind of goes together, and then motor control in order to actually move something. And key challenges coming along with this is a not comprehensive list, I'd say, which we compiled. Specifically looking at batteries, there's battery modeling, there's safe operation of batteries, battery aging, and of course, BMS development, developing the software to safely and efficiently operate those batteries. So I just like to start out quickly going actually to MATLAB Simulink and showing you a high-level overview of the things we can do. So I'll go over here. So this is now Simulink model, which is part of our shipping documentation, in fact. So this is something that everyone who has our tools can take a look at. I guess the key thing is there's this button called Run. And if I run this, it's going to perform a dynamic simulation of my system, which consists of a battery equivalent circuit. So there's a physical modeling part. In orange, we have thermal components. So there is a temperature source, there is heat transfer. In blue, we have the electrical part. We have a voltage sensor and a current sensor here, as well as hidden inside this block an equivalent battery circuit model. And then on the right-hand side, we have a state of charge estimator. I took this example because it's one of it's well known and well established that state of charge estimation is a critical part of a BMS. So this model can be used to simulate behavior of a battery, electrical and thermal. Can be used to also develop and simulate a Kalman filter. And this is then the results. So we can visualize simulation results, and we can see the yellow line is the real state of charge, and in blue we have our estimated state of charge. Of course, there's measurement noise added to this to add more realism. And yeah, we can run this simulation of our system, and this is basically what Simulink does. Just to quickly give a bit more background, this is a script that comes along with this Simulink model, and it really explains in a lot of detail what exactly is happening, how exactly the model is being developed. So yeah, you see it goes on for quite a while. So it's not just a basic thing. I think this already contains quite a lot of detail on developing such a state of charge estimator. So yeah, that's that. I'd like to quickly also talk about 3 user stories from customers of MathWorks. First, on the left-hand side, this is a company called About Energy. And what did they do with our tools? So they used MATLAB and Simulink to create a battery model for fast charging. So fast charging, of course, it's kind of a key topic nowadays in the electrical mobility space. And this company combined like custom thermal single particle models together with equivalent circuit models modeled in Simulink and Simscape, which allowed them to do a multi-scale approach where they could start with individual cell modeling and scale up to entire pack simulation. So this company used our tools for modeling and simulation of the physical battery components. Second company is a two-wheeler, used to be a startup. Now it's grown a bit more, from India, called Green Tiger. So apparently India is one of the largest markets for these two-wheeled vehicles. And of course, all of them are still gasoline operated. So they started to hybridize them. Instead of going to full electrical, they provided a way to retrofit existing two-wheelers to hybrid two-wheelers. And here, what they did is they had to develop a BMS, mostly a robust BMS for charging, cell balancing, pack initialization, etc. And in this case, they worked together with us, with our consulting, to establish a structured methodology for developing battery pack models, parameter estimation, and then the entire BMS algorithms. And finally, there's a third story here, which is from Zaft. It's a French company. And they were developing, bigger batteries, which you can see here. And this, the highlight of this story is more around actually getting towards safety, critical operation, and certification. Because of course, we all know batteries, if not operated properly, become pretty dangerous. And functional safety and certification of the BMS software is critical. And some key highlights here is that through using the tools and model-based design, the methodology of model-based design, they could reduce the time needed to develop and certify the BMS software by more than 50%. So they were twice as fast using this methodology than before. They leveraged hardware-in-the-loop testing, and of course desktop simulation as well, instead of directly going to prototypes. So they could identify issues earlier on in the design process. And they managed to pass this UL 1998 certification in the first attempt as a result. I didn't just choose these user stories by accident because they kind of fit the three overarching topics that I want to present today. The first one is physical modeling and multi-domain dynamic simulation of batteries. Then there's BMS development, so more the algorithmic side, and then I want to touch a bit on exactly this deployment, function safety, certification aspect of the BMS software. The key message, I guess, is that MATLAB Simulink, they act as a central platform for the entire workflow, starting from physical modeling and simulation, then developing algorithms, and then deploying and industrializing these algorithms. So Simscape Battery is kind of the focus, I think, of the first part especially. What is Simscape Battery? I'll just quickly open a link. So Simscape Battery is one of our add-on products, which sits in Simulink, and it offers a lot of functionality to design and simulate battery and energy storage systems. I think this page gives a pretty good overview. It kind of repeats what I've said before. It goes from cell and pack modeling. There's a big focus on cooling, BMS, and then testing and deployment. There's a lot of resources already available here. So as I said, Simscape Battery can use, design, and simulate battery energy storage systems. You can model electrothermal cell behavior. You can use it for battery pack design, BMS development. You can use it to evaluate pack architectures for electrical or thermal requirements, develop and verify your BMS algorithms, and also leverage it for hardware-in-the-loop testing. So the battery models which are developed in Simscape can be deployed to real-time computers and then integrated in Hill setups. Some key features, the battery pack builder. I'll get to that a bit later. So starting from cell models is one thing, but at some point we need to not just simulate single cells, but also packs. And there's a very neat battery pack builder functionality to do that, help us with that. There's cooling, it's a big topic, and their cooling plate models are key features of Simscape Battery, as well as a host of BMS algorithms which come out of the box. So there's a variety of standard BMS algorithms that establish themselves nowadays, and we have made them easily available for our users so they don't need to develop them from scratch. And of course, finally, again, there's support for C code generation. So everything that is being created in Simulink for a BMS can then be transformed to C code and deployed to embedded systems. So physical modeling, starting out with a cell. I guess the most basic component from our point of view, at least, of a battery. Oh, a bunch of, there we go. So there is the standard way how we as MathWorks look at a battery is using a battery equivalent circuit model. So we have a multi-domain physical model where we have the electrical cell model, which is being modeled as a standard approach, right? It's this kind of a RC circuit approximation. There's different levels of detail available. You can have 1, 2, 3, or many of these RC circuits. You can do hysteresis. And then there is a thermal lumped cell model to do the thermal part of this. So the cell is a lumped thermal mass. And of course, there is power losses which generate heat. And there can be heat coming in from the environment, which affects, again, our electrical characteristics. So MATLAB Simulink, we don't do like the very detailed chemical simulation, right? So this is maybe an important point to make here. We also don't do FEM simulation of thermals, for example. It's one level more abstract. So we lose a bit of fidelity, but it enables us to take the simulation from single cells all the way to the complete system, and then to integrate, of course, all the algorithms that go along with it. So just to situate our tools a bit in this landscape. One other important aspect that of course comes in again when we talk about developing BMS, there is also the capability to simulate faults in a cell, faults in a pack, so like short circuit faults, thermal runaways, these kind of things. Of course, this capability is critical when developing the BMS, because then you need to test it against various scenarios and prove that the BMS will work. When it comes to creating battery cell models, of course, you can start from scratch, but often you will buy a cell from a manufacturer. You will not be the company who also makes the cells. So what we have implemented is a quite comprehensive list of pre-parameterized components. So we've taken the most popular battery cells, and we have, essentially created an easy way for you to just create a cell, click like this is the cell I have, and it's going to pre-populate all the important characteristics, so you don't need to do that on your own. Or, of course, if you have a custom battery that's not in our list, or if you want to refine the parameters that come out of the datasheet, there are ways to adjust that on your own. Just looking here at this battery equivalent circuit model, maybe let me just quickly jump back over here. This is what we have here actually. So there's a battery equivalent circuit model, and we can see there's a quite large range of parameters. So it's a block. It looks pretty innocent, but when you open it up, we can see there's capacity is kind of the main characteristic. There's various ways to do thermal modeling. Either just say there's no temperature dependence, or then start to let's see. Exactly down here, start to add some thermal mass to the battery. We can start to adjust electrical circuit parameters with temperature. There's capabilities for aging, cyclic or calendar aging, fault simulation down here. And just jumping over here, this is a link to the documentation. Again, I think it's a pretty good way to get an overview. We see this single block here has a very big doc page on, well, the electric model, as I mentioned, is these RC circuit equivalent models. And then, it goes down a long way, talking about temperature modeling. For example, there's a possibility to model short circuits, as I mentioned, or thermal runaway behavior in a cell, and so on and so on. So today, it's definitely not the goal to do a deep dive into how exactly all these parameters work, but I'd like to give you just the impression of this is not just a simple RC model that runs with fixed parameters. It's a very powerful block that enables you to simulate batteries to a very high level of detail. So this is just for your further reference as well, probably because we're going to share the PDF all of this. So there's a bunch of links down here as well. Pretty new in our toolbox nowadays is also the capability to not just do these empirical equivalent circuit models where things are approximated as RC circuits, but also to do electrochemical modelings at some level of detail. Now, a small disclaimer, I am not at all an expert in this topic. So I cannot really go into what exactly the capabilities are here, to be honest. But again, there is a link here. And if you're interested in how this simulation is being implemented, you can follow the doc page, and there's a good explanation there. But this has been an often requested features by our users, that we not only provide the empirical ECM model, and so this is something that starts to come up. Of course, the trade-off is always between performance and fidelity, so we're trying to bridge the gap here. So that's individual cell modeling. Of course, then the next step is going from a cell to a pack. And this is where this battery builder functionality comes in. So the video runs very quickly through it. Essentially, we start from a cell, which we characterize according to our specs. And then we can start to build a parallel assembly. There's 10 cells, for example. We can start to combine assemblies to a module, and then all the modules to a pack. So the video is, yeah, it's been very, very quick. And the key functionality is, in the end, when the pack is created, it generates a library block, and then you can just insert this block in your Simulink model, and it's gonna run. Yeah, and that's it. So you don't need to manually connect hundreds of cells together or write your own scripts. There's functionality to assemble cells to modules to packs. You can import existing battery objects as well. Of course, there's these nice plots to give you some visual validation that what you're assembling is actually what you're looking for. And of course, this was the graphical interface. This can also all be programmatically accessed. So this is what it looks like when you finalize a module or a pack. It's just going to be a nice, neat, simple block. In Simulink, of course, you can then go and look beneath the block, and you will see all the details and how things are wired up. There's a bunch of ports, essentially, which can then be exposed. There's, of course, the electrical connection of the battery pack. There can be thermal paths to ambient, so the way that heat is exchanged with your ambient. There's imports for balancing signals, and there's the possibility to add thermal cooling plate paths as well. So you can see it allows you to very efficiently model and simulate battery packs at this system level. Of course, there's always a trade-off between calculation speed and precision. So it's about choosing the model fidelity. There can be a detailed model. Now, this is for thermal modeling, just to be clear. So there's detailed modeling where each cell is modeled as its own thermal mass, as well as its own electrical. It's both thermal and electrical. Sorry about this. So either each cell has its own characteristics, its own components. It can be a lumped or it can be a grouped model. So you can kind of divide and conquer in order to get the fidelity and performance that is appropriate for your designs. And when it comes to thermal paths, there's thermal paths outside the model. So there's convection and conduction of heat to the ambient, essentially, or there can be thermal path to cooling plate as well, and both of these can be modeled quite easily and are available with these blocks. There's also, of course, then thermal paths within the module. So there's the inter-cell paths where cells kind of conduct heat to each other, as well as intercell radiative paths where they radiate heat to neighboring cells. One important aspect is, of course, in a battery pack, not every cell is made equal. So there's a straightforward way to add variation to all essentially every parameter of a cell. So you can start to randomize and make these pack models more realistic by adding a percentage-based deviation, for example, of internal resistance or open circuit voltages and pretty much everything else. So you can start to model a pack where, yeah, each cell is modeled to a high level of detail and is also differing for each other. And especially when it comes to aging and these kind of things, this also becomes very relevant. Finally, what you can do when you have such a complete system simulation, you can, for example, here do a thermal as well as SOC and current visualization, where some cells are being charged up, and we can see on the left-hand side how the temperature evolves over time. So yeah, it's a very powerful tool to visualize as well the behavior of your pack and really get this visual confirmation that things work the way we expect them to. Next comes the cooling plate part. I want to just lose a few words on this. If we have battery pack like this, we offer out of the box a bunch of ways to add cooling plates. There's a bunch of standard designs which we have implemented. There's, for example, on the X side or on the Y side is kind of what it's called here. Cooling plates can be attached to these different sides. And then there can be forced convection, so you can just enable this in your block. So simulating a cooling plate on one side, you can have, it kind of looks like this then, of course, then plates on the side with cells on the side with the cooling plate will be cooler. We can have thermal loads for all sides, so you can start to add forced convection for each side of the pack, and you can see how this affects temperatures. There's ways to add serpentine plates, so kind of cooling plates that loop around our different cells, single or double-sided. And we provide a bunch of cooling plate topologies out of the box, edge cooling, parallel channels, or U-shaped channels, which again can make you get set up quite quickly for these designs and simulations. Then moving on from the physical modeling part. So we have ways to build cells, ways to build a pack, way to add cooling. So now we can move on to the actual BMS algorithm design part. When it comes to battery management algorithms, as I mentioned previously, there is a range of provided blocks with Simscape battery and in general with Simscape and Simulink. There's algorithms for charging and discharging, for enforcing current limits. There's a block to do passive cell balancing. And there's estimators, state of charge, state of health. It starts with simple Coulomb counting and goes all the way to Kalman filters, linear, extended, unscented, etc. There's protection mechanisms for overcurrent or voltage and temperature monitoring, as well as fault qualification. And there are thermal management blocks for coolant and heating control. And again, in this slide, there's a small link. There's a reference list. So here you can see all the battery management systems blocks that are being shipped right now. You can see it covers most of the aspects, I guess, of a standard BMS here. Of course, the power of Simulink is you don't need to just move and go with what we provide. You can always build your own blocks or extend the existing blocks as well. Yeah, to customize all these to your specific needs. One specific tool I want to highlight, which is very valuable for BMS design, it's called Stateflow. It's a graphical language which you can use to model and simulate state machines and flowcharts. And it's fully integrated with Simulink and MATLAB. So we can see on the right-hand side, it's in a very intuitive way. It starts at the top. This is for a cell balancing algorithm where we enter first the balancing of state. And then if some condition starts to be true, we move to another state where something else happens until, again, some conditions are true. And these kind of systems, it's pretty hard to develop these and debug these if you don't have this kind of graphical flowchart representation. And this screenshot, again, is actually taken from a shipping example here, which is a battery management system algorithm, which leverages a lot of state flow to do all the key aspects. So you can see there's fault detection, there's general battery operations management, etc. Stateflow is powerful because it doesn't just visualize. It's not just like VZO where you can draw things. It can also simulate. So if you start a simulation, it's gonna animate the state it's in. It's gonna animate transitions. You can set breakpoints. You can use it to debug your logic. And there are formal edit time and runtime checks and tests to ensure there's essentially completeness. So you can do coverage. You can prove that your tests have covered all the states and all the transitions. You can prove that there's no deadlocks in your state machine, that you don't get stuck anywhere, that there's no transitions that cannot be reached, that all the things have been tested. And yeah, when you move on to the topic of functional safety and certification, again, this is of course a critical capability. Yeah, and putting all of this together in the end, it really allows us to create comprehensive simulation models of complete battery systems. Like see in this screenshot here, we have module with a battery module with a cooling plate attached to it. So there's a physical component, multi-domain physical dynamic simulation here. There's a coolant controller. There's a state of charge estimator. And we can simulate all of this in the closed loop, visualize all the states of our battery, compare the performance of our estimator with the real physical states. Yeah, everything we need to develop a BMS system. And once that's done and our BMS system works well in simulation and passed our tests, and we believe that this is something we want to go and start to deploy, of course, we don't deploy MATLAB or Simulink on an embedded processor. So that's where automatic code generation comes in. Moving on to deployment, we have a very powerful suite of tools to translate essentially MATLAB and Simulink code to C, C++ code, to HDL code for FPGAs, to CUDA code for GPUs. So this allows you to move from this high-level language, which makes debugging simple, it makes development fast, and then you move to embedded targets through C, C++ code generation. This is a very tried and tested approach. It's been around for 25 years now or more. It's being employed by many companies in Switzerland and abroad to make development and deployment fast. Functional safety is another thing. This is just a very kind of a teaser slide, I guess. There's different standards across different industries, and our deployment workflows support certification. Essentially, there's tools that enable you to generate C code and also generate necessary documents and proofs and certificates that the code, that the code matches and these standards. So it makes this step a lot more efficient. Again, harking back to the user story, which I mentioned in the beginning, where they stated that they could cut the time by 50% to get certification. One important aspect before just generating C code and hooking up your code to real battery is hardware in the loop testing. So if you're not familiar with this concept, the goal is that, or the idea is you have your desktop simulation, everything works well. So you generate code for your BMS, you put that BMS on your embedded target, but then before connecting that embedded target to your real battery, you connect it to a simulated battery. So you can also generate code for your SimScape model, the physical model of the battery. You deploy it to a real-time computer, which has all the right ports, all the right interfaces as the real battery, but it's still in simulation. And this is an intermediate step that guarantees that the algorithm runs as intended on your embedded device. And if this step is passed, you can then go on and you connect it to a real battery. And the advantage is if something still goes wrong, you know that it's not an error in the deployment process, but it's an error in the algorithm itself, essentially. So you need to go back to Simulink and adjust your algorithms. It's safer as well. If you programmed any bugs, you won't blow up your battery by accident. You'll just blow up your virtual battery, and this is a bit less stressful for everyone involved. There's a YouTube video which I'd like to link here as well. As I mentioned, we'll share the slides, so we'll have this link too. This is by our partners at Speedgoat in Bern. They're also here in Switzerland, and they provide actually real-time hardware. So they interface very well with our tools, their partners, and this is a very cool overview video of exactly this hill testing of battery management systems. So they will go into much more depth here. Okay, so I'll not use the full hour, which I guess is also just as well. We'll have time for some questions. So I want to finish up with again, these three overarching topics. So I give a very fast run through of physical modeling, multi-domain simulation. So model battery packs, model the dynamics, electrical, thermal, then developing BMS systems, and then this whole deployment aspect. I want to leave you with a bunch of resources, which can be, which I hope are interesting. There's a pretty great white paper which my colleagues wrote on developing battery systems in Simulink and Simscape, which goes through the topics I presented today a bit more, with a bit more time, a bit more slowly. There is a free on-ramp course. If you're interested, you want to just check it out, this Simscape battery tool, and give it a try yourself. You need to register, I think, a MathWorks account, which is free, and then you can launch this small course. It's all in the browser, no need to download anything, and it takes 1, 2, 3 hours, and it's going to really run you through these topics. You'll develop a bunch of Simulink models on your own, and you can really get a feel for what the tool does yourself. A bit more formally, there is also an official training which we offer. If you're interested in this, please reach out to us, specifically to Raghu, I'd say. And this is something where our trainers can help you to properly ramp up and transfer all the knowledge for the tool. And then finally, there's a collection here of links on the next page, video series and documentation pages on batteries. And I think that's it. And thanks everyone.
Thank you, Christoph. Thanks a lot for the wonderful presentation. I would like to add from my side, before throwing the floor open for Q&A, if you guys are interested in having a dedicated discussion on the battery management system or the workshop, we are glad to organize that a couple of hours with Christoph and our other technical experts, either on-site, online, or you're always welcome to visit our office in Bern. So that's a complimentary service kind of technology workshop that we can organize for you to understand if our tools could be of value for your product development or for your workflow. And along with that, we can also offer you a free trial license in case you would like to define a proof of concept project and work together with us. With that, I throw the floor open for questions.
Yeah, thank you very much, Christoph and Raghu, for the insights and the deep dive to the tools of MathWorks. So, as usual, to everybody that wants to ask questions, please raise your hand virtually, and then we can open the microphone for you that you can ask the question. Yes, we have a question from Vincenzo. Well, Vincenzo.
Yes. Do you hear me, guys?
Yes. Yeah. Good afternoon.
Thanks. Good afternoon to everybody. I was just wondering if you can please give us some more hints regarding the model parameters. So implemented in the battery model. So how those parameters have been identified and how the model accuracy is somehow evaluated, which range the model validity is.
Yes. So that's, of course, I guess, the crux of the thing, right? If you use the pre-parameterized ones, which I mentioned in the beginning, it's just whatever's available in the data sheet of the manufacturers. But it's actually something I realize now that I didn't put in the presentation. There's, of course, also all the workflows where you can leverage data from experiments, and you can use this to optimize and fit your model parameters. So there's workflows. I think I can try to dig up some links. I know there are some good examples on this. Essentially, it uses optimization. You can say, yeah, this is my initial guess for my parameters. Now optimize the parameters to fit my recorded data. Yeah, and then validating as well against, of course, then the standardized tests.
Clear. Let's clarify a lot. And if I can ask also, I mean, you say there are some say hints or possibility of simulating something related to aging. This is a kind of linear aging. I mean, which kind of age? When you talk about aging, what is behind?
So there's the cyclic as well as calendar aging, and as far as I know, for cyclic aging, you can have an equation based. So there's some fit depending on number of cycles, or you can provide lookup tables, temperature dependent or independent. I'm just looking at what the block provides now, to be honest. When it comes to calendar aging, I'm a bit less sure myself because I know this gets pretty dicey.
Exactly.
Yeah, but I can actually ask my expert colleague. He's on vacation now. Otherwise, I would have looped him in for these questions. But I'll ask him, and I'll provide some information afterwards.
And those, I would say, both performance and aging prediction are based on MathWorks job, or it's a joint activity with some external institution, for example.
If you would like to do aging prediction as an algorithm, or how do you mean?
No, I mean the model behind. I mean, it's something that you develop internally, or somehow you use some.
Well, essentially, people developing our tools usually have a background in research, and then they leverage, of course, what's out there research-wise. Yeah, we don't have like an official industrial partner like a battery manufacturer like this, because otherwise we probably couldn't share whatever we develop with everyone else. Yeah, but essentially we leverage what's out there in academia and implement these things.
Thanks a lot, really. Thanks.
Thank you.
Yeah, thank you, Vincenzo. Are there further questions from the audience? We would still have a bit time for Q&A.
I see a bunch of people who know the tools better than I do, probably, so they don't have questions, I guess.
Yeah, maybe some of them. I have a question now. Mostly, you showed us in the presentation cylindrical cells.
Yes.
Is there the possibility to basically model any shape? Well, there's limited ways of having battery cells, right? But are there different possibilities, like also, for example, modeling a blade cell or something like that?
Yeah, so I know there's cylindrical, there's prismatic cells, blade, I'm not quite sure, pouch cells as well. There's 2 or 3 different options, but I need to go and find exactly what they are. But it's not only, actually there's cylindrical, pouch, and prismatic are the 3 that are supported right now.
Yeah, and then you can just adjust the dimensions basically according to
Yeah, essentially the dimension is kind of abstract, because in the end what you parameterize when it comes to the heat transfer is kind of the thermal resistance or conduction between your cells.
Okay. Yeah.
Which then depends on many things, of course. It's also something that needs to be characterized somehow, so it's another thing of estimate the parameters properly, I guess.
Okay. And I think I think we had a small discussion, or you showed that at the MATLAB Day, that there is also the possibility to implement code outside, right? Made outside from like from Python or something.
Yes.
Maybe can you say a few words about how that can work, or how this or maybe how can you implement other tools in the network?
Well, essentially, see my screen again. There's what we call the external language interfaces. So you can call libraries outside of MATLAB written in C++, Python, I guess is the two most common one. If you're brave, you can go and write things in Fortran and also still call that as well. Exactly. So it's a very, I think it's very mature way now, and they made some big simplification in recent years to enable this. I know some people have started to put in Python, and Python is kind of the big one, I guess, for high-level things. And then, of course, if you have already existing algorithms in your BMS, then C++ is usually the way to go. And that's very straightforward. I mean,
But there could be a possibility for Vincenzo's question before, right? To the calendar gauging. So if this is not directly available,
yes,
you could implement that as a Python or C++ function into the model.
If there's some open source library exactly which you have access to, and then that's straightforward exactly. Or something someone made in academia, you want to give it a try. No need to translate that.
Excellent. There is one more question or remark from Lorenzo. Great to have you here. Ciao.
Hello, can you hear me?
Yes.
Hello, Christoph. Thanks for the presentation. One small question regarding the modeling. I mean, you showed that now Simscape Battery included an SPM. I think this is something really recent. Be like,
yes.
Do you have plans to also extend these to also have a full DFN model, for example? Or what is the plan in the electrochemical modeling track for Simscape Battery?
There's two things here. I don't know myself, and I probably wouldn't be allowed to tell you here in a public forum, but I can definitely find out and send you more info on that. Yeah, I know that you, amongst other people, I think, asked for this last time, right? And
yes, I wanted to know if there is some update, but if you if you want to say in a different forum or just with among
I'll
us, we
figure
can
it out
discuss
and let you know. Yeah, exactly. Thanks.
Okay, thanks for this one. I would give it one last chance for asking a question, and otherwise I would stop the recording and thank once again to MATWorks. So I hope to see you next, either at the workshop, annual conference, or the next webinar that we will have Imaris talking about the topic of graphite. So thank you very much, everybody, for being here, and see you soon.
Thanks, everyone.
Thanks, everyone.